All right, thanks again, Ed. We'll give you another virtual applause here.
Thank you.
And then our next speaker is, I think it's Felicia. Let me find my agenda here. Yes, Felicia Sutanto. I saw you in the room, Felicia.
Yep. Okay.
Perfect.
Can you?
So I can hear you. Your slides look great. We can see everything. So again, our next speaker is Felicia Sutanto. She is a fourth-year student at the University of Michigan, studying with Professor Igor Yovanovich. And today she's going to talk to us about the SAND detector, which is another approach for directional antineutrino detection. So Felicia, the floor is yours.
All right. So good morning or afternoon. My name is Felicia Sutanto. I'm a graduate student at the University of Michigan, and today I will talk about a solid-state antineutrino directional detector called SAND. So I want to first introduce our team. 3 different institutions are involved in this project: University of Michigan, University of Hawaii, and Lawrence Information Laboratory. We are working together in this project, and so having introduced our team, I'll start by explaining what motivates this project. So conventional safeguard practice focuses on material redundancy and surveillance to track the full assemblies, and such practice is costly and also time-consuming for both the agency and also the reactor operator. We rely on operator declaration, and there is no direct return inventory measurement made until the fuel is reprocessed. And so there is a motivation to develop a method where we can monitor process status of reactor directly, not intrusively and continuously. Now, reactor is the most intense man-made source of antineutrinos. There are 6 antineutrinos generated per fission in average. And for a typical reactor, we have about 10 to the 21 fissions per second. That means a typical reactor, it will produce about 10 to the 22 antineutrinos that are emitted in all directions. If we place 1 ton water volume about 10 to 50 meters away from the reactor, we'll detect about hundreds of antineutrino events per day, assuming we have 10% detection efficiency. So this number goes down really fast, and that is because antineutrino has a very small interaction cross-section. So they just pass through a large amount of materials unimpeded. Now, while this makes their detection challenging, it also means that they cannot be shielded. So that makes them attractive candidate for reactor monitoring, which is very well aligned with the NNSA mission. So remote reactor monitoring using antineutrinos is an established technology. For example, SONGS, Nucifer, they have successfully demonstrated reactor monitoring using antineutrinos. And the way they detect antineutrinos is via the inverse beta decay reaction. So this reaction produces a positron and a neutron. The positron annihilates, and that creates the first burst of lights. And the neutron thermalizes, and it's captured by a neutron capture agent, and that creates the second burst of lights. So antineutrino signature is 2 bursts of lights that are correlated in both time and space. Reactor monitoring using antineutrinos, they offer several advantages. They operate continuously, non-intrusively. They also directly measure the thermal power of reactors, which constrain the fissile content. And traditionally, these detectors, they are deployed below ground to suppress the cosmogenic background. But below ground deployment is expensive, and it limits the available space. And so to mitigate such issue, current interval detectors are typically segmented, and they employ pull-shape discriminating material to isolate the delayed coincidence and to reject the accidental backgrounds. Now, what is shown here, these are the above ground near-field detectors that have successfully demonstrated reactor monitoring using antineutrinos. They are Panda, Minichandra, and Prospect. And the order of these detectors, they show progression in achieving a convincing demonstration. You can see that the ratio of on-off rates, it gets better and better. So they have been successful. But one thing that has not been offered by these detectors is directionality. And directionality could be important when there are more than 1 reactor present or when there is a hidden reactor. SAN is currently the only near-field detector that employs homogeneous lithium-doped PSD capable plastic. And we focus more on a finely grained segmentation to obtain better spatial resolution that allows for directional sensitivity. So the central module of SAN is an 8x8 array of 0.5 by 0.5 by 40 centimeters lithium-doped PSD rods. The central module is surrounded by plastic bars made of the same material and with a larger cross-section. And the central module is instrumented with 2 CPAM arrays to collect lights at both ends, and the outer module is instrumented with 2 PMTs mounted above and below the plastic. We have built the central module of SAN, And we have produced 1 bar of the first outer layer and 1 bar of the second outer layer. In this talk, I will call the central module component 1, and 1 bar of the first outer layer as component 2, and 1 bar of the second outer layer as component 3. Now, when antineutrino undergoes inverse beta decay, positron and neutron are created. The positron carries most of the energy, but the neutron carries most of the forward momentum. And therefore, the direction of antineutrinos can be approximated by drawing a vector from the position of the positron interaction to the position of the neutron capture as shown here. We will attempt to identify and remove backgrounds based on pull-shape discrimination, rod multiplicity, electron equivalent energy deposit, and time and position correlation. Okay, so we have characterized the sand components and few performance metrics were studied. I took measurement with a Californian source and I optimized the pull-shape parameter based on the figure of merit, where figure of merit is defined here. And what is shown here is the pull-shape parameter light upper response of the central module. We observe triple PSD here, where the top band corresponds to the fast neutron interactions in the detector, and the lower band corresponds to the gamma ray interactions in the detector. We also observe the capture island that corresponds to the neutron captures in the detector. And this is important because we need to identify the position of neutron capture to get the directional information. The associated figure of merit as a function of light output is shown here. At 1 MeV, we observe figure of merit around 0.7 for component 1 and about 0.8 to 0.9 for component 2 and 3. I also took measurements with a cesium source to investigate the energy resolution of the sand components. Component 1 shows energy resolution of about 22% at the component edge of 62 keV gamma rays. And component 2 and 3, they show energy resolution of about 18% at the component edge of 62 keV gamma rays. We also have developed a Gen4-based simulation framework, and we validated our Monte Carlo by comparing our simulated light upper response to the measured data. And as shown here, we observe pretty good agreement between the simulated and the measured responses. We do observe discrepancy in the low energy region, and this is caused by the low energy scattered gamma rays that were not present in the simulation. We also validated our Monte Carlo by comparing the simulated and the measured apparent attenuation lengths. I took series of collimated cesium-137 measurements along the synclinary axis to obtain these attenuation length plots. And simulations were then tuned to maximize agreement between the measured and the simulated attenuation lengths as shown here. We observe measured apparent attenuation lengths of approximately 18 centimeters, 28 centimeters, and 31 centimeters for component 1, 2, and 3, respectively. For component 1, the loss of light is dominated by the reflection losses because component 1 has a high aspect ratio. For component 2 and 3, intrinsic absorption length of the plastic also greatly affects the penetration length. Now, just for comparison, the length of sand is 40 centimeters. So these attenuation lengths, they are about half to 3/4 of the length of sand. Now, of course, the attenuation length affects the Z position resolution. We observe Z position resolution of about 2 to 3 centimeters at 1 MeV. And again, just for comparison, these neutrons, they travel about 5 to 7 centimeters in our detector. And so this Z position resolution, the Z position spread is less than the average distance traveled by neutrons in our detector. Okay, lastly, rod multiplicity. Particles can be identified not only based on the PSD, but also based on rod multiplicity. And this is possible because different particles, they have different range. So what is shown here is a simulated rod multiplicity distribution for IBD neutron and IBD positron. A clear difference between neutron and positron can be observed. Most of the neutrons, they only trigger one rod. And most of the positron, they trigger multiple rods. And such difference can be used to differentiate between different particles. So what is shown here is the current cuts that I use to estimate the antineutrino detection efficiency. For the neutron capture cuts, I fitted a Gaussian profile to the measured capture island, and I use a 2 sigma cut. So that's what these cuts are. For the PSP, I chose the cut such that the misclassification probability is constant at 1% for all energies. And majority of capture, they only light up one rod. So I set the cut such that a capture event must produce rod multiplicity equals to 1. To identify the a positron-like event, I applied an energy cut greater than 1 MeV. That's because below 1 MeV, the PSP does not look very encouraging. And I also apply an upper energy cut at 7 MeV to exclude the muon events. The PSP cut was chosen such that, again, the misclassification probability is constant at 1% for all energies. And lastly, for the multiplicity, it either has to be greater than 1 in the central module, or it has to be greater than 0 in the outer layers. And then the time cut. So this was obtained from both the background data and also IBD neutron simulation in the full SAN detector. We optimized this cut based on the shape of the inter-event time distribution. And we determined the best cut to be around 45 microseconds. And just for comparison, the average neutron capture time in our detector is 36 microseconds. So using these cuts, I could then estimate the anti-neutron detection efficiency. And the efficiency is currently estimated to be like about 19%. We are interested in deploying our detector either close to power station or a research reactor. The Hartlepool reactor in the UK, it has 2 cores, each is 1500 megawatt. There is a laundry room about 15 meters away from the core, and we could potentially place our detector there. And detection rate was estimated to be like about 0.9 per day. Example of research reactor is Hyfer at Oak Ridge. The reactor power is 85 megawatt. There might be a spot about 70 meters away from the core, and I predicted detection rate to be about 2.5 per day. Now, one thing that I have not talked about is SAN directional capability. So I simulated inverse beta decay interaction in SAN, and what is shown here, these are the constructed positron-neutron vectors. So our detector is segmented, so you'd see some features here caused by the segmentation. Now, many detectors such as Ghost Gun, Palo Verde shows, more recently Double Chooz, they have theoretically and experimentally studied their directional sensitivity to anti-neutrino flux. And so far, among all of these detectors, Double Chooz reported the lowest angular uncertainty of 43 degrees for 100 detected inverse beta decay events. SAN is predicted to have a better directional spread in comparison with Double Chooz. I'm not showing the math here, but you can calculate it from the numbers that are highlighted in red here. We predict that SAN will have angular uncertainty of 25 degrees for 100 detected IBD events. Okay, so currently we only have 1 bar of the first outer layer and 1 bar of the second outer layer of SAN. The journey of producing the first lithium-doped PSD bar has been challenging. Lithium compounds absorb the light from the polymer. Also, since polymerization is exothermic, we need to be careful in controlling the temperature for large volume. And what is shown here is our early efforts. But since October 2018, we have successfully produced a large sample of lithium-doped PSD bars. So hopefully when we regain access to our lab, we can produce the rest of the bars and complete our detectors. Okay, so just to conclude my talk, reactor monitoring using antineutrinos has been demonstrated many times. However, the ease of deployment certainly needs to improve. SAN is segmented and employs pull-shape discriminating solid-state material. This could potentially allow SAN to be deployed above ground. And further fine segmentation of SAN leads to better spatial resolution, which is critical for directional sensitivity. We have built our central module, and we have produced 1 bar of the first outer layer and 1 bar of the second outer layer of SAN. We have characterized them. We validate our Monte Carlo by comparing our simulation results to the measured data. And using such simulation, we can then predict the performance of full SAN detector. And SAN is predicted to have a better angular uncertainty in comparison with Double Chooz. SAN offers above ground directional detection that is of interest of non-professional community. This research is conducted in collaboration with the University of Hawaii and Lawrence Information Laboratory. Through such collaboration, I have fostered a strong working relationship with the postdoc and staff scientists at Livermore and colleagues at University of Hawaii. So thank you. I'll open it to questions.
Thank you, Felicia. Very nice presentation. We have a few comments popping up in the chat, so I will do my best to interpret them. The most recent question asked about the efficiency. So you mentioned a calculation of the efficiency to be around 19%. So the question is asking about how that's defined, and can you just comment more about how you got that number?
Yes, so that efficiency is obtained by simulation because we have not taken data with antineutrinos yet.
Okay, and is it intrinsic efficiency, or how is it defined?
So that is the efficiency of detecting if antineutrino comes to detector. That's the efficiency of detecting the antineutrino via the inverse beta decay reaction.
So for all neutrinos that are incident on the detector, simulation suggests you detect around 19% of them.
Yes.
Okay, makes sense. How close and how many counts per day? I think this question was about, you were talking about proximity to reactors,
Yeah.
and how many counts per day you would achieve in those situations. So can you speak some more along those lines?
So it depends on like which reactor and what is the distance from our detector to the reactor. So I think I had 2 examples. Let me go back to that. So currently I do the approximation for 2 sites. The first one is at Hartlepool reactor. It has 2 cores, each is 1500 megawatt, but actually for this approximation, I only consider 1 core. There's a launcher room about 50 meters away from the core, and we can do the math from there. And then if we apply the 19% detection efficiency, we'll get about 0.9 per day. But that's one example. Another example is Hyver at Oak Ridge, and there is a spot potentially like maybe like about 7 to 10 meters away from the core, and I estimate the detection rate to be about 2.5 per day. Yeah, so I guess it depends on like what reactor, like what power reactor we're looking at, and the distance to the reactors.
Yeah, that makes sense. Thank you. Another question asks, are these simulation measurements? I think, I'm not sure which results Ahmed, you're referring to. You can chime in if you want to specify, but I think everything you showed was simulation, right? Was there any measured data in the presentation?
All of the calibration, this is all measured, but the result for the IBD, they are all simulations because we have not taken data with antineutrinos yet. But all of the calibration, those are real data.
Right. Great. I had a bit of a naive question about inverse beta decay. Maybe you can help me with. So in the beginning, you were talking about the reaction process, and you said that the positron and the neutron were correlated in both time and space. So time correlation makes sense to me. The spatial correlation I don't quite follow, because it seems to me that as the neutron thermalizes, you would kind of lose the spatial correlation. So can you talk a little bit about that?
Yeah, that's right. So like this neutron, they're thermalized, so they're actually like kind of losing their direction, but they still carry that forward momentum. So you cannot do it, at least like with our current system, you cannot do event by event reconstruction. But what you do is that you will have like statistical measurements. You would need many data in order for you to point to where the reactor is. So it's not an event by event reconstruction. You will have to need it's statistical measurements. It loses its direction, but it still carries that forward momentum a little bit.
Mm-hmm. That makes sense.
I think there is another question.
Yeah, a question about, so from an non-pollution standpoint, does the detector have to be on site to do this type of monitoring that you were suggesting in the introduction?
Yeah, it has to be close enough to the, so, you know, in a sense that you would need cooperation from the reactor when you do near field detection. When you do far field, then you may not, you don't need the cooperation from the reactors, I guess. But for near field, I guess like it also depends on like your phone. But I would guess that for near field, you know, you're talking about like some liters, like tens liters of detector. You probably would need to be close enough to the reactor.
Right. So it's a trade-off, right, between how close you need to be and how large the detector volume.
So currently, so STEM is about 9 liters. And I would say also, I guess like Mini Chandler has done it, and I think Mini Chandler is like about 20-30 meters. So I would say that maybe for near field detector, less than 50 meters. And typically, like the size of near field detectors, like tens of liters. SEN is actually 9 liters, but you know, like 10 liters. But typically, the size is like, you know, tends to like 10 liters or like 100 liters, I think.
Yeah, I had a question along those lines actually about the size of the detector. So I think you said it was 40 centimeters in length. So I was wondering, you know, and you were talking about the Z position reconstruction and kind of the challenges related to that. So I was wondering how you arrived at the 40 centimeter length, and also just the size of the detector in general. So can you comment on kind of how those dimensions were chosen, and also is that design scalable in any way? If you wanted to make a larger version, could you use modules or scale it in some way?
Yeah. So currently the reason why it's only 40 centimeters is because our oven can only handle 40 meters length of plastic, cannot go longer than that. But we have purchased a new oven actually, and there is actually an effort currently at Livermore to scale this detector larger to like 1 meters. And we actually have done studies on like its intrinsic absorption length. And we think that distribution length is probably like about 70 centimeters. So if one can actually make the surface of this plastic smooth enough that you don't lose lights from the bouncing off the surface, so 1 meter seems reasonable actually for like 72 centimeters increase absorption length. But yeah, it's scalable, and there's actually an ongoing effort to scale that up.
I'm just reading this most recent question from the chat. So the question is, in a kind of a more real world scenario where you have a nefarious actor who's trying to, hide a reactor or defeat your system, how would this approach be applicable in those situations?
Yeah,
kind of a broad question, but maybe you can give us your thoughts.
Yeah, so this is an interesting question actually. So like it has directionality, but if you have like two reactors like side by side, then you would see like shape in X and Y, for example. But like say if you put the next like the other detector like 180 degrees from the other reactor, then you might cancel out and you probably wouldn't see the shift in the direction. So in that case, it might fail. What you would need is the cooperation from the other reactor.
Yeah, interesting. Okay, well, thank you, Felicia, and thanks to all those that asked very good questions. And I think we'll move on.